In this video, we are going to learn how to calculate equilibrium concentrations. So when we say equilibrium concentrations, these are the concentrations of the products and reactants when an equilibrium is established. So ICE is a suggested method for solving equilibrium concentrations. I stands for initial concentration. So how to determine the initial concentration? Usually, this is given. Oh, okay, this is given. But for the case of our product, it is assumed that initially the concentration of our product is 0. Why? Because at the start, we don't have product yet. But sometimes, the concentration of the product is specified because there are cases in which there is an initial amount of product that is placed in the mixture. Then the amount of product that will be produced by the reaction will be added to that initial concentration to get the concentration of the product at equilibrium. Then C stands for the change in concentration. So all you have to do is to assign change as the variable x, and then we will use the stoichiometry of the reaction to assign changes for all species. Anyway, I'm going to show this later. Then E stands for equilibrium concentration. So to get the equilibrium concentration, all you have to do is to add the initial concentration and the change. And of course, you have to take note of the different signs of your x or the change in concentration. Okay, later, I am going to show you. Okay, so for us to be able to understand this concept, because I know it is difficult to understand this without an example, let us solve this example. Okay. For example, we have this reaction. Okay, when 250,000 mole of sulfur dioxide and 200,000 mole of oxygen gas are placed in a 10-liter vessel at 1000 Kelvin, the equilibrium mixture was found to contain 162,000 mole of sulfur trioxide. Calculate the equilibrium constant for this reaction. Okay, so remember that when we solve for equilibrium constant, the concentrations that will be substituted to our expression must be the concentrations at equilibrium. So first we have to set up our ICE table. Okay, so we have our reaction. Okay, okay. So let us write here the initial concentration, our I. Okay, and then the change. Okay, so what is the initial concentration of sulfur dioxide? So as stated here, you have 250 mole of sulfur dioxide in 10 liters. So to get the concentration of sulfur dioxide, divide 250 thousandths by 10. And that is, okay, 0, that is 25 thousands mole per liter. Okay? How about your oxygen gas? You have 200,000 divided by 10, so that is 2 hundredths or 0.02 mole per liter. Okay. Now, how about our product, sulfur trioxide? So, understandably, we don't have sulfur trioxide at the start. So, therefore, the concentration of sulfur trioxide, the initial concentration of sulfur trioxide is 0 or 0 mole per liter. Now, how about the change? Now, we don't know yet, okay, how much of this amount of sulfur dioxide, and oxygen gas are consumed prior to equilibrium. So, as stated earlier, let us assume that the change in concentration is X. Okay? This is X. This is X. Okay? And how about this one? This is positive X. Okay. Why? Why is it that this is negative X? This is negative X because this is the amount of sulfur dioxide that is consumed. So this negative symbol here means that this there is a certain amount of your reactants that is consumed by the reaction. And what will happen to that reactant? Of course, that reactant, this a certain amount of sulfur dioxide will combine with certain amount of oxygen, forming certain amount of sulfur trioxide. That is why this is positive. Okay, because this is the amount of sulfur trioxide that is formed from certain amounts of sulfur dioxide and oxygen gas. Okay, I hope that it's clear. Okay, why the sign is negative for reactants and positive for products. So at equilibrium, okay, what will be our concentrations? Okay, so as stated in the problem, at equilibrium, you have 162,000 mole of sulfur trioxide. So therefore, the concentration of our product sulfur trioxide at equilibrium is, okay, that's 162,000 or 0.162 divided by 10, that is 0.0162 mole per liter. So this is the amount of sulfur trioxide that is present at equilibrium. Now our question is, what will be the concentrations of sulfur dioxide and oxygen gas at equilibrium? Okay, so that's the question now. Before we can solve the concentrations of our reactants at equilibrium, we must know first the change in concentration. Yeah, yes, because our equation here is concentration at equilibrium is equal to the initial concentration plus the change in concentration. Okay, so we have to solve for x first. And as stated earlier, we have to use the ratios, the stoichiometric ratios of the species. So what is the ratio you have here? For every 2 moles of sulfur dioxide, you need 1 mole of oxygen gas to form 2 moles of sulfur trioxide. Okay, that's the ratio. So therefore, if we have if we have 0.162 mole of sulfur trioxide, then how many moles of sulfur dioxide and oxygen gas are consumed to form this amount of sulfur trioxide? Okay, so you have here. Okay, let me write here the, sorry. This is our coefficient. These are our coefficients. So you have 2 for sulfur dioxide, 1 for oxygen gas, and we have, okay, again, in order to produce 2 moles of sulfur trioxide, we need 2 moles of sulfur dioxide and 1 mole of oxygen gas. Then according to the problem, at equilibrium, we were able to produce, okay, 0.162 mole of sulfur trioxide. Then therefore, how many moles of sulfur dioxide? So if the ratio here is 2 is to 2, if you're going to reduce that, that is just equal to 1 is to 1. So therefore, the amount of sulfur dioxide consumed is, okay, and this one is half of 0.0162, and that is, okay, why? Because for every 2 moles of sulfur dioxide, you only need half of that, and that is 1. So if you have 0.0162 mole of sulfur dioxide, you need half of this amount in order to produce 0.0162 mole of sulfur trioxide. So these are the changes in the concentrations of our products. Okay, so now, sorry, what is the concentration, I mean, of each species at equilibrium? Okay, so at equilibrium, you have, for sulfur dioxide, you have 0. Okay, the formula is just to add. So you have 0.25 plus negative 0.162. And that is 0.00880 mole per liter. So we just use the formula. Concentration at equilibrium is equal to initial concentration plus the change in concentration. And since our change in concentration is negative, so that becomes 0.025 minus 0.0162, and the result is this one. And then for oxygen gas, you have 0.012 mole per liter. Okay, so we have now the concentrations at equilibrium. So to solve for the equilibrium constant, so all you have to do is to substitute in the equilibrium expression. So our equilibrium expression is K sub C is equal to concentration of sulfur trioxide raised to the power of 2 divided by concentration of sulfur dioxide raised to the power of 2 times the concentration of oxygen gas. Okay, substitute. We have, okay, mole per liter raised to the power of 2 divided by, okay, what is the concentration of sulfur dioxide at equilibrium? It's 0.0, okay, raised to the power of 2, okay, divided by, okay, mole per liter. Okay, then use your calculator. Don't forget to square the quantities, and then you have here 282 liter per mole. Okay, so this is the value of the equilibrium constant at what temperature? Is the temperature specified for this problem? At 1000 Kelvin. Okay, now I am going to give you more examples. Okay, please wait for the next video.